Hello, everyone, and thank you very much for attending this webinar. So my name is Sergey Khaykin. I am an associate professor at University of Versailles, Saint-Quentin, which is located near Paris. And I am also a research scientist in the LATMOS laboratory, which is located at the same place. So I will talk today about the Arctic polar vortex and its impact on weather and climate. So this is the content of my presentation. So I will first explain you what is the polar vortex and what it has to do with the ozone hole in the Arctic and the Antarctic. I'll also talk about the link between the Arctic polar vortex dynamics and surface weather. And I will show finally some examples of experimental studies related to the Arctic vortex. I'd like to make this webinar fully interactive. So if you have any questions during the presentation, you can raise your hand and I will make a pause to answer them. Okay, so as you may know, the atmosphere includes several layers which differ very much by the chemical composition and thermodynamical properties. So the lowest and the most important layer of the atmosphere is the troposphere. That's where we live. This layer extends from the ground up to about 10 kilometers altitude. That's the cruising altitude of the commercial jet aircraft. And the layer above is called the stratosphere. It extends between about 10 and 50 kilometers altitude. And so the stratosphere is the home of the ozone layer, which protects us from harmful ultraviolet radiation coming from the sun. And it's also the home of the polar vortex, which is the subject of this webinar. So in order to understand this atmospheric phenomenon, we need to first consider the atmospheric circulation at different layers of the atmosphere. So this looped animation here, it shows the wind fields at the surface as of yesterday. So it's near real-time situation. And the color map indicates the wind velocity, which you can also infer from this animation. So this information on the state of the atmosphere is provided by meteorological measurement networks and also by operational satellite observations. And all this data are processed by highly elaborated numerical models, which are used to provide the weather forecasting and nowcasting. Nowcasting is the real-time information on the weather. So if you look at these wind fields at the surface, you can see several synoptic weather systems such as cyclones, which rotate counterclockwise, and anticyclones, and they are very variable in time and space. But you can also see here persistent circulation patterns. For example, the Mistral winds here in the French Provence. Now, if we look at the wind fields at 10 kilometers altitude, we will see very different circulation pattern, which is characterized by strong and very variable wind flow. And these are the so-called jet streams with wind velocity up to 200 kilometers. So you can see that it's really very different from what we have at the surface. Now, if we go even higher, to 30 kilometers, which is already well in the stratosphere, you will see a steady circulation pattern, which is a very large cyclone above the Arctic. And this is actually the Arctic polar vortex at its present state. Okay, now I'm guessing that we are ready to discuss the general definition of the polar vortex as such. So first of all, it is a huge cyclone. Cyclone is a low pressure system which forms in autumn when Arctic or Antarctic temperatures above the pole cool rapidly as the polar night begins. And then the increased temperature difference between the pole and the tropics causes the strong winds, and then the Coriolis effect causes the vortex to spin up. So the stratospheric polar vortex breaks down in spring as the polar night ends, and right now we are at the end of the Arctic vortex season. Regarding the vertical extent, the polar vortex extends throughout the entire stratospheric layer between 10 and up to 60 kilometers altitude, or maybe even higher. And it's characterized by very strong eastward winds, which reaching 400 kilometers per hour. And these strong winds, they act to confine the air inside the vortex, and as a result, it becomes isolated from the other parts of the atmosphere. And also because it occurs during the polar night conditions, the air confined within the vortex does not receive much heating from the sun, which leads to a strong cooling of air in the stratosphere inside the vortex. And this cooling gives birth to a spectacular atmospheric phenomenon, the polar stratospheric clouds, which are exclusive to the polar vortex because of its extreme coldness. And what I should note here is that the stratosphere is very dry, and normally it doesn't allow clouds to form. But in the extreme cold of the polar vortex, however, the stratospheric clouds like those that you can see in these images can form. And because they allocated at very high altitudes between 15 and let's say 25 kilometers, these clouds will receive sunlight from below the horizon and then reflected to the ground, which makes them shining brightly well after the sunset, as you can see in this picture. So this polar stratospheric clouds, or PSC for short, they play an important role in the springtime ozone depletion. I will talk about the ozone in the next slide, but what I need to say here is that these clouds, they provide a surface on which the chemical reactions leading to ozone destruction can occur, and this results in an ozone hole or ozone layer depletion above the poles every spring. So these clouds are more abundant in the Antarctic vortex, which is colder than the Arctic vortex, and also the Antarctic vortex is characterized by a stronger ozone hole. So at this point, it is important to briefly remind you the story of the ozone hole and its discovery. So it was discovered in the 1980s, mostly from satellite observations. The satellite observations of the atmosphere have started in the 70s. And then during the 80s, the satellite measurements of the ozone layer, which are shown in this plot year per year, they were showing strong indications of the depleted ozone layer above the South Pole since 1979. The values that the satellites have been suggesting were so low that they have been initially rejected because they were just hard to believe. And then once this data was reprocessed and the scientists have saw how deep is the ozone hole above the Antarctic, this realization came as a shock to the scientific community because the observed decline in polar ozone was far larger than anyone had anticipated. So these concerns led to the adoption of Montreal Protocol in 1987, which took into effect in 1989. And this protocol, as you probably know, banned the production of ozone-depleting chemicals. And since then, the Antarctic ozone levels have stabilized and started to slowly recover, as you can see in this figure. And the ozone levels are projected to fully recover by the end of this first century. Now, it's actually still quite a big issue whether those projections of ozone hole recovery are accurate enough. So this issue is still a very hot topic in atmospheric science. So now, what about the situation in the Arctic? Well, what needs to be understood here is that the Arctic stratospheric vortex is much weaker than its Antarctic counterpart, and this is due to the fact that the Arctic region is basically the sea surrounded by land, whereas the Antarctic is the land surrounded by sea. And as a result, the Arctic vortex is much more prone to dynamical perturbation and is therefore less stable and less cold. And this can be illustrated with these figures here, showing annual temperature variation above the northern and southern polar region. And as we can see, the Arctic vortex temperatures are warmer. You can compare values here, and they are also strongly variable over the course of the winter, as opposed to the stable and cold Antarctic vortex. Nevertheless, over the recent decade, the Arctic vortex was showing some unusual behavior, and during some of the recent winters, the Arctic ozone hole was quite important. So, the long-term continuous measurement record of the Arctic ozone layer is provided by a network of ground-based instruments located in different countries, as you can see on this map. And from this data, every year we derive the wintertime evolution of the Arctic vortex ozone layer. As shown in this figure, you can see how the ozone layer is being depleted progressively over the course of the winter. And you can also see that in the years 2011 and 2020, the ozone loss was anomalously strong. And as a matter of fact, the year 2011 ozone hole was unprecedented in the observation record since 3 decades, as you can see in this figure. So it looks as if the probability of such extreme events when the Arctic ozone hole becomes quite important, the frequency of this event seems to be increasing, and we don't really understand why it is happening. Now, what we know is that the amount of springtime ozone depletion in the Arctic strongly depends on the sub-seasonal evolution and the dynamics of the Arctic stratospheric vortex. And what drives the dynamics of the polar vortex is the large-scale atmospheric waves, which are generated by the jet streams and which are also generated above the continents. So this is more the case in the northern hemisphere. So these waves, they can propagate towards the polar region and perturb the vortex. So therefore, weakening the vortex and the ozone depletion process. And such event, when the vortex is strongly perturbed, is called a sudden stratospheric warming. and it occurs every 3 to 5 years in the Arctic. So what happens during such an event is that the vortex is perturbed and the Arctic stratosphere is rapidly warming. So here the bottom three figures represent the polar projection map. So the pole is here in the center. So these are the maps of potential vorticity, which is a measure of rotative motion, and it is therefore proportional to the strength of the vortex. So the left-hand figure reveals a strong and stable vortex, like it was the case in 2011 when the ozone hole was anomalously strong, and the two other figures show cases of perturbed vortex during a sudden stratospheric warming event, and these events can be classified as minor SSW, which is strong but short-term perturbation of the vortex, which changes its shapes and may displace it temporarily from the pole to lower latitudes, whereas during a major SSW event, which are more rare, but they lead to breakdown of the vortex in two parts, or maybe even more independent parts, as you can see in this figure. So such events not only reduce the degree of springtime ozone depletion by warming the stratosphere, but they also affect the surface weather, and it was the case this winter. So this animation here shows the evolution of the Arctic vortex since October 2020, when it has started to build up. So you can see by looking at the color scale how the colors are getting more intense, which means that the rotative motion is getting stronger. So now we are in December. We see that it is mostly centered about the pole. Sometimes it gets elongated, but retains its integrity. And then close to the new year, it was displacing a bit. And now here you can see that it is perturbed. I have two parts. It's strongly displaced towards the south. So that was a major sudden stratospheric warming event this winter. And there was actually two, one in January and the other one in February. So one part has been torn out of the vortex, and then a smaller part has survived, and it is still there, but it's weaker than it usually is by this time of year. Well, what needs to be understood regarding the link between the polar vortex and the weather is that the vortex itself will not appear outside your front door. It doesn't influence the winter weather directly, but it's more like a domino effect. When it's knocked over, it can start a chain of events that later result in wild weather, as it is illustrated in this figure. So when the vortex is perturbed, or when it's shifted from the pole, it affects the jet stream, and more specifically, it pushes it south, which leads to the transport of cold Arctic air towards the south, and this causes a very cold winter in Europe and the United States. So the strength of the polar vortex can vary widely during the winter, as we have just seen in the previous slide, and these variations can lead to shifts in the strength and in the position of jet stream, as you can see in this plot. So to remind you, the jet stream are the fast a flowing river of air in the troposphere, which is beneath the vortex, but they are dynamically connected, and when the jet stream changes, it affects the movement of weather systems, causing different parts of the world to see much warmer or much colder conditions. And these plots here show how a weak or perturbed stratospheric vortex affects the weather conditions in the northern hemisphere. So it causes cold extremes in Europe and US, dry spells and flooding in Europe, together with extreme winds in Eastern Atlantic. Obviously, understanding the Arctic stratospheric vortex dynamics is very important for the seasonal and subseasonal weather prediction, because as you can see, such events, they have a very large effect on the society, and even can kill people, as it was the case this winter. So the progress in understanding of the dynamics of the vortex, it owes to the growing computing capacities, which allow to run the numerical models at higher resolution. However, it would not be possible without the experimental research of the atmosphere. And this brings me to the last, but certainly not least, part of my presentation, where I will talk about the atmospheric observation techniques applied in the Arctic region and elsewhere. So there exist many different types of observation techniques and measurement platforms. In particular, we can talk about the satellite remote sensing, then the ground-based remote sensing, which is done using active and passive techniques, the ground-based in situ measurements, which means local measurements. For the stratosphere, what is more often applied is the weather balloons. I will talk about them more later. The large stratospheric balloons and the research aircrafts. So the weather balloons, they provide the crucial information for weather forecasting. And the approach here is quite straightforward. It is to attach a simple sensor package to a balloon filled with a lifting gas like helium or hydrogen, and send it into the atmosphere. And that's how it looks like. These soundings, they are conducted within the worldwide network of radio soundings, and they are conducted once or twice a day. So they provide the vertically resolved information on the basic meteorological parameters such as pressure, temperature, humidity, and wind speeds. And these data are collected through radio transmission on the ground. So what happens during the flight of such balloon is that as the balloon is a closed envelope, and as the pressure in the atmosphere decreases with height, the balloon is expanded, and then at 30 kilometers altitude, this balloon, which is this big on the ground, it expands to a diameter of 10 meters. And then when the rubber, which is the material used for that, can no longer withstand the pressure, the balloon explodes, and then the sensors come back to the ground. And this is a video which is recorded from such a balloon. You can see the view from 34 kilometers altitude. So it looks pretty much like space here, because there is not enough air molecules to scatter the sunlight. So this is still when the balloon is ascending. It's very calm, and now it's about to burst. So that's the balloon burst, and now it's starting to fall down with a very very high speed until the parachute unfolds to to slow down the descent. So that's how it looks like from this point. Now, another way which is extremely useful, especially for the studies of the Arctic vortex, is the so-called long-duration balloons. They have a closed airtight envelope, which is made from plastic, which is very robust and does not explode. So these balloons, they stabilize at a specific altitude, somewhere in the stratosphere, and then they're just being carried by an air mass, so they behave like a parcel of air in the atmosphere. And there were several campaigns in the Arctic where we have been launching many of these balloons, and this animation shows the track of these balloons inside the polar vortex for several days. And this is a launch of such a balloon with the instrumental payload. So, and then this particular balloon, it has made a full circle around the pole, and then it was landed safely not far from where it was launched from where it was launched from, and this is how the payload recovery looks like. So you have to use the helicopters and go deep into the Lapland forest. Another type of the measurement campaign activity is the aircraft-based research, and I will quickly tell about a big international campaign which was held in 2010 from Kiruna in Sweden, and it involved 8 countries, 16 institutes, 22 scientific instruments, and with a total cost of this activity nearly 5 million euros. So that's how much this research costs. So this is a map of the flight tracks, and this video shows the takeoff of the stratospheric research aircraft, which is a very rare aircraft capable of going as high as 22 kilometers, thereby reaching the stratosphere. At the same time, we had a balloon campaign in Sodankila in Finland, and the idea is that the balloon launch time is coordinated with the flight of the aircraft, so that the goal is to sample the air masses which are going in this direction twice, first with the aircraft and then with the balloon. And this way you can get an idea on the evolution of the chemical composition of the air mass, which was sampled first by the aircraft and then by the balloon. Okay, I'm going to skip this slide, and just a few words about the satellite remote sensing platforms. So the very good thing about the satellite-based measurements is that, unlike the local measurements, they provide a full Earth coverage, so you can get information on what is happening in the Earth's atmosphere globally. And what needs to be understood is there are 2 types of satellite orbits which are used for atmospheric research. So there are geostationary satellites which are located at high altitude orbit, and they rotate with the same speed as the Earth, staying fixed over one spot above the equator. But as far as the Arctic region is concerned, more relevant satellite orbit here is the so-called polar orbiting satellites, which stay at a lower orbit and which sample terrors, like you can see in this animation. So they provide a full coverage in 3 to 15 days, and they provide many observations at high latitudes, as you can see in this figure, which shows the ground tracks of the satellite orbits, and you can see they are very dense in the polar region. So we have a lot of very useful information from this satellite. Okay, and this brings me to the summary. So I'll just walk you through the main points I wanted to convey. So the Arctic polar vortex is one of the largest circulation system on Earth, which occurs every winter over the North Pole, and well, there is a very similar Antarctic vortex, which which occurs during the opposite months. And then what needs to be retained about the polar vortex is that confinement and cooling of the air inside the vortex leads to formation of high altitude clouds in the stratosphere, which trigger the springtime depletion of the ozone layer. This depletion is much more important in the Antarctic, but as I have shown, the ozone hole may also be the case in the Arctic when the vortex is stable. When the vortex is unstable, like it was the case this year, we can see that the dynamics of the vortex affects very strongly the weather patterns in Europe, in North America, and can cause extreme cold and snowy weather. So, and this is why understanding the factors of the Arctic vortex dynamical variability is crucial for subseasonal weather predictions and also the climate projections. And this is why observations using Earth and space-based platforms are indispensable for understanding the processes and their evolution in the Arctic stratosphere. We can also have some indications that the stratosphere in general interacts with climate change in an unexpected way and reveals new feedbacks. Recently, what we are seeing is that the wildfires have become more and more intense, and we can see that the wildfires can have a large and long-lasting effect on the stratosphere, which in turn has important feedbacks on the polar vortex, on the ozone layer, and also on the surface climate. So this is one of the perspective topic of the research related to the Arctic stratosphere. And I will stop here, and I'm ready to take your questions.
Thank you, Sergey. It was really fascinating, really amazing what you told. And we can see that it has effect on people, even though we think that it's up there and we don't have to care.
Exactly.
It has effect, as we saw this winter. Will that be the case also in the future, that we will have these extreme weathers every now and then?
Okay, the answer is that we don't really know, and that's the big issue. We are not even able to predict such events on a 1 or 2 week advance, and not to mention the predictions for the seasons. What we see is that well, basically with the climate change and the global warming, there are more and more extreme events with the surface weather, but we are also seeing that there is an increasing number of extreme events in the stratosphere, which has a link. So all the feedbacks, they are quite complicated, and the realization is that our current knowledge and understanding may not be sufficient to make accurate projections of the future climate and the behavior of the atmosphere.
Hi, Sergey. It's Kirk here. Thanks for that. It's really packed with a lot of really interesting things.
Thank you.
Just a quick question, a couple little things. One, historically, do we have the history going back far enough to say we're in an unprecedented time? You know, like 200 years ago. It's a, does archaeology tell you anything? Second question would be, what happened in 2011? Seems to be something there. Mm-hmm. And I'm wondering about the effect of microplastics on the atmosphere. History 2011 and microplastics. That's it.
Okay. Well, so of course, we don't really know what has been happening with the stratosphere. Let's say in the 19th century, because basically this layer of the atmosphere has been discovered in the very beginning of the last century, when the first radio zone has reached these altitudes, and we have seen that the temperature doesn't decrease all the way with altitude, but at some point it starts to increase back, which is mostly due to the absorption of solar light by the ozone, which makes the temperature to rise in the stratosphere. So to answer your first question in a more concise way, no, we don't have records about the stratosphere before the middle of 20th century. We don't really know whether this has happened in the past or not. The surface temperature record is much longer than that, so we can try to associate some extremes in the surface temperatures based on the longer historical records, but that won't be enough to really say whether there are any connections or not. So we still miss some historical information, which actually makes it more difficult to understand what will be in the future. So if that answers your question, I will go to the second one. What happened in 2011? Well, basically, it was a record high ozone hole in the Arctic, which became comparable in a way to the Antarctic ozone hole. There was a lot of buzz in the media about that, like this picture. I know that's actually this year, but you can see from this record that it was really much stronger than in the other years. So why this has happened? Just because the vortex, the Arctic vortex in this winter was very strong and very stable. So it was not subject to perturbation like it was the case this year. So basically, it was a very strong vortex, which had an opportunity to cool down. And as I was explaining, the cooling leads to the polar stratospheric clouds, and their abundance leads to enhanced ozone depletion processes. So this is what happened in 2011, and this was also the case in last winter, not this one, but last winter, which where the ozone hole was almost as big as in the record year of 2011. And your third question was regarding the plastics.
Yeah, like we understand, we see microplastics in life forms and in the soils. I'm just wondering, given the fact that plastics can become infinitely small, is there an impact of those in terms of the atmosphere or the vortex? I'm just thinking. Right?
Well, basically, speaking generally, the surface emissions, whether that would be microplastic or whatever, they affect the chemical and aerosol composition of the atmosphere, which have the radiative effects. So it affects the radiative balance of the atmosphere, and of course it affects in some way the ozone chemistry. So basically, yes, but I'm not sure that the effect was very well quantified yet.
Right. Thanks very much. I really appreciate your presentation and your answers. Thanks.
Thank you.
Are there any other questions or comments? No. I think that you gave us a lot of food for our thoughts, really, and understanding that this, how big is the kind of that how everything is connected. And
Yes.
and what we do and see here in our everyday lives is actually affected something much bigger. It's yes, and we all know some movies that are based on, for example, this polar vortex breaks down, which I think that I would like to watch again now once I have heard this presentation. I don't remember the name of was it 2012 or something like that. I don't remember the name of the movie, but
yes, I know which movie you're talking about.
Yeah.
Yes, well, of course, this movie was a big exaggerate. The climate change cannot be this fast, but these extreme events, which don't last forever, they can be quite severe, which is what we are witnessing.
Yeah. Yes. And yes. So and yes, I understand that that's a movie and it happens very quickly, but kind of gives an idea of what happened, for example, in US this year, and the Beast from the East.
Yes.
Was it in the UK a couple of years ago? Yeah.
Yes. So basically, each time it gets very cold in the US and very snowy in Europe. It is in each case it is related to the perturbation of the jet stream, which are caused in turn by the perturbations of the vortex. And then the perturbation of the vortex are caused by the planetary scale waves, which may be generated in the tropics. So you can see that everything is very tightly linked in our atmosphere. So it's hard to predict the effect of one perturbation, how it can propagate through the atmosphere and have consequences which are not at all obvious.
Yes, thank you. So thank you very much, Sergey, and Janette will edit this a bit and then let everybody in our networks know about the presentation, and you as well, of course, Sergey.
Okay. Thank you very much.